To help us really get a feel for the Heisenberg uncertainty principle, I'd like to try a second example. Now, the motivation for the second example is that you might actually have some possible objections to the example with the lens. So for one thing, we saw how the principle was obeyed, but that doesn't really prove the principle, right? It might be that one objection is that we could design a better experiment, right? Just because one setup doesn't give us very precise results or has a limit doesn't mean that we couldn't find some other experiment that would get us down to something even more fundamental. The second thing, and I'll put a question mark here because we don't know if we could design such an experiment. The second thing is that, well, that one seems to depend a lot on that photon, right? It seems to depend on properties of the probe. Which is the photon. Maybe if we use something instead of a photon, right? Seems to depend on properties of the probe, not of the particle itself. So to try to resolve this, my second example is going to be something where there really is no kind of a probe. I want to get down to seeing if it's really more a fundamental property of the particle itself. So the second example to get rid of the probe is going to be an example of single slit diffraction. And I'll show you in a moment exactly how this works and why I think it doesn't have this issue that it's being probed and that there's a probe involved. So the idea for this one is a standard single slit diffraction experiment. So I'm going to have some kind of a source, and just for fun, let's make it electrons. Although, as we're saying, all of the de Broglie hypothesis is the same for all these different particles, but let's focus on electrons. So I've got my source, and we'll say all the electrons are coming out of this source in different directions, right? But they're all going to have the same energy, E, right, which is p squared over 2m, so that I know, in fact, the momentum of all of these electrons. Now, then, further away, I'm going to have a screen with a slit, and I'm going to make my slit larger in my diagram so we can do some interference analyses. So here's a single slit screen. And of course, over here, I'm going to have a photoplate. Now, we know what happens when we do this experiment. And of course, you need to imagine the source is very, very far away, so that when the electrons are coming in, there's not enough room here on my screen to draw how far away this needs to be. The idea is that it's far enough away so that when the electrons actually make it to this slit, it's very clear that they're all traveling in the same direction. Now, we know what's going to happen. There's going to be these electrons are coming in with some wavelength, h over p, and they are going to experience a standard diffraction pattern. So we're going to get a single slit diffraction pattern, which means the electrons will arrive at random locations on my photoplate, sometimes up here, sometimes down below, but the overall pattern has to follow what's familiar to you from a single slit diffraction pattern, something like so. So those are the results from the experiment. Fine, so we do this experiment. Now you might ask, well, where is the measurement? So the measurement has to do with the electrons as they emerge, as they first emerge from that slit. And the idea is, as they first emerge from this slit, I've effectively done a measurement of their position. right? Because I could put my x-axis, say, right here, like so, right? And so when they first emerge from there, I've effectively measured their position because I know, well, I don't know exactly where they are, but I have a pretty good idea where they are. And if I were to do an immediate follow-up measurement of where they are, I know they have to be somewhere along the profile of that slit. So the follow-up measurement of the position is going to give me a range of different results, which I can call P of x. And I know there's no probability, right, that they had positions out here, outside of the slit. So let me get some width here for my slit. I'll call my slit here width D, right? So then where the follow-up measurements will put them is all somewhere between D over 2 and minus D over 2. Right? So I've measured their position. I've measured that it's basically 0 to within a range minus D over 2 to plus D over 2. And then there's a range of outcomes. So according to Heisenberg, then that delta x is going to equal, again, I'm not doing a formal integration over this probability distribution. I just know they're equally distributed in here because the electrons are all coming, smoothly straight on in. So delta x in this case, I'm going to call d over 2, which is basically the width of that distribution. Now, there's also a follow-up measurement, and this is a little more subtle, but it's interesting. So there's also a follow-up measurement of the momentum. Measurement of px. Now that measurement may be a little bit more mysterious, but notice, right, we know the electrons were all coming straight in, right? So if they didn't have some x momentum, they would have landed right down the middle of that distribution. But instead, they land over a range of values, right? So, and where they land, so, if he lands at this angle here, right, or some other angle, right, wherever he lands, I can use that in a right triangle to determine the x component of the momentum. So I simply need to draw a right triangle with the angle theta of where he landed, right? And now I want to know this, which would be the x component of my momentum, because remember, I've drawn my x-axis vertically. And I need to know then my hypotenuse. But my hypotenuse is my total momentum. And the thing to notice is that the energy of these particles, right, they just go through my slit and then they come out in a diffraction pattern in different directions. There's no energy transfer between them and the slit, so they have the same energy over here as they had when they were incoming. And because energy is p squared on 2m, that means the momentum, the magnitude of the momentum, is the same as it was when they were coming in. So this is just p. And then my momentum measurement is px equals p times the sine of that angle theta. Now, of course, we know we get this diffraction pattern. So there's going to be a range of these different angles theta. So there's actually going to be a range of different momenta that we will be measuring. So there's going to be a probability distribution once again for these momenta, p of px, right? Most of them are near zero momentum because they just traveled straight through with an angle of 0, right? And there's a peak there, and then of course it has these little bumps in it. So there's going to be some probability distribution like this. And that distribution then has some variance, right, and some standard deviation, which I could, and one day we will, calculate formally. But for now, I just need to sort of estimate how wide this distribution is. And I think a good estimate would simply be to estimate the range here as the theta, the angle that gives me the first minima in my single slit diffraction pattern. So that tells me then delta px will equal the momentum of the incoming particles times the sine of this first diffraction minimum. Now, all we need to do is to determine that, so we have to recall a little bit of our single slit diffraction. And you may recall how this works, right? If I really want the condition that I hit this minimum, I want the following to be true. Remember, we have these different path lengths that come from different points in the slit. This is the center point of my slit. This point down here, say, is the bottom of my slit, right? And then what we do is we consider all of the outgoing waves from all of the little points along our slit. And they each have different path lengths, which you can determine by dropping this perpendicular. So we know that the remaining paths are equal. So the path difference between these two paths is the length of this side of this right triangle. We know from geometry that, of course, this distance is d over 2. And if I'm looking here at diffraction across an angle theta, I can see that this angle is the complement of theta, so this is the angle theta. So this extra path length for these two paths is d over 2 times sine of theta. But I want to find the condition for theta min. Now, to get this minimum, what I need is for there to be cancellation. So I can arrange that this path is exactly half a wavelength longer than this path if I set this condition. That half wavelength would mean this point and this point are 180 degrees out of phase. It also means if I go up a little bit here and up the same distance here, these 2 points, which also are at a separation of d over 2 away from each other, would be destructively interfering. And you can continue the argument. And what you begin to realize is that for every point in the upper half of the slit, there's an exact out-of-phase point in the lower half. And this is the condition for the minimum angle. So if we copy our condition down, we had d over 2 sine theta minimum. That is the change in the path length between the upper and lower halves of the slit. We want that to be exactly lambda over 2. We can cancel the 2's. We then can divide both sides by d and can replace this distance as lambda divided by d. So my momentum uncertainty is the momentum of the particles times their wavelength divided by the width of my slit. Now it's time to do a little quantum mechanics because we know that p and lambda are related. The momentum of the particle is p. The wavelength of a particle is h divided by p. And then we, of course, have our d in the denominator. Our p's will cancel. We have h over d. That will be the range, then, of our follow-up measurement of the momenta. So when we narrowed the particle down to have this more narrow distribution in position, what ended up happening is associated then with our superpositions of waves, we find there's a spread in the momentum in this amount. And you'll notice, again, there's tension. To make a precise measurement of the position, I want a very narrow slit, so I'll know that the particle is exactly at 0. But if I make a very narrow slit, I end up with a rather large uncertainty in my momentum. And the product of the two, delta x, delta px, in this case, the uncertainty in x was half the size of my slit. The momentum was h over d. So the momentum, excuse me, my pen is acting up a little bit. The momentum was h over d, and the product then is h over 2, which once again is very safely greater than h bar over 2, the fundamental limit. And again, I stress, this is an approximate analysis that we've carried out. Very nice. So we see again how this type of experimental setup shows us that even after what we think is a pretty precise measurement of something like the position by using a narrow slit, we end up then with a wide spread in the values of the follow-up measurements of the momentum in the x direction.